allotrope is simply a different form of the same element, each with distinct physical and chemical properties. For example, oxygen can exist as diatomic oxygen or as ozone. These molecules are made exclusively of oxygen atoms, though their structures and properties are very different from one another. This allotropism can also exist in certain metalloids and metals. Silicon is a very important element. Silicon is used in circuits of many electronic devices, such as your mobile phone and laptop, and in solar cells. Silicon exists in crystalline form and in non-crystalline form, also known as amorphous silicon. In crystalline silicon, silicon atoms are arranged in a tetrahedral structure, with each atom covalently bound to 4 other atoms. Here is a challenge for you. Which allotrope of carbon has the same tetrahedral structure? Pause, think, and continue when ready. The answer is a diamond. Each carbon atom is covalently bound to 4 other carbon atoms in the same tetrahedral arrangement. Amorphous silicon is non-crystalline silicon. In this structure, the silicon atoms are not held together tightly like in crystalline silicon. Crystalline silicon and amorphous silicon can both be used to manufacture solar cells, which are grouped together to make solar panels for solar-powered electricity. One day, all cars may run on solar power, and homes cooled or heated with solar panels. Considering that fossil fuel is a non-renewable resource, solar-powered electricity is now at the forefront of innovation and research. Another metalloid with many allotropes is boron, each with its own unique structure. We know that iron and its alloys are very important in everyday life. Iron is a great example of a metal where allotropism is present. Each allotrope has a different structure, which gives rise to different properties. The interesting concept here is that these different allotropes arise at different temperatures and pressures. So one allotrope of iron can change into another allotrope. The 3 most common allotropes each have a cubic structure. Alpha iron and beta iron and delta iron each have a body-centered cubic structure. In this structure, there is an iron atom at the center of the cube, which is linked to all 8 iron atoms at the vertices of the cube. Another allotrope of iron has a face-centered cubic structure. In this structure, there is an iron atom at each face of the cube. At very high pressures, another allotrope of iron is formed, with a hexagonal close-packed structure. Some other metals that exhibit allotropy include lithium, sodium, calcium, and titanium.